going to start now. Good time to start. And this is EE Colloquium or ECE Colloquium, but people are invited from all over campus, and I welcome you all. And because this is part of our LIDA lecture series, which is today. And when we discussed who would be our LIDA lecturer this year, I suggested that we try to get the best signal processor that I've ever met, who also happens to be having great impact in machine learning. And I thought that would be broadest interest. And we're fortunate to have him here. He's a good friend of mine. And in spite of his busy schedule, unfortunately for us, he accepted, and he's here. And his name is Stéphane Mallat. His PhD is from University of Pennsylvania in 1988. After that, he became a professor at Courant Institute of Mathematical Sciences. In 1995, he became professor of applied mathematics at École Polytechnique, Paris, and department chair there in 2001. From 2012 to 2017, he was a professor in the computer science department of ENS in Paris. Since 2017, he has held a data sciences chair at the Collège de France. His research interests include machine learning, signal processing, and harmonic analysis. He most recently introduced something I found very interesting, which is a scattering transform that constructs invariants for recognition. He's a member of the French Academy of Sciences, a foreign member of the US Academy of Engineering, an IEEE fellow, a URSIPCO fellow. In 1997, he received the Outstanding Achievement Award from the SPIE Society and was a plenary lecturer for the International Congress of Mathematicians in 1998. He also received the 2004 European IST Grand Prize, 2004 INIST CNRS Prize for Most Cited French Researcher in Engineering Computer Science. And I just checked Google Scholar, and he's almost at 100,000 citations now, a huge number. So that's really impressive. He also has a 2013 Innovation Medal of the CNRS, 2015 IEEE Signal Processing Society Best Sustaining Paper Award. So he's had broad impact in many areas, not just in signal processing. So I'm so happy we have him here. And this morning he's going to be talking about interpretable deep networks for classification, generation, and physics. Stéphane.
So thank you very much for this very warm welcome and for the pleasure of being here. As Les said, in some sense, I moved from applied mathematics, signal processing to machine learning about 9-10 years ago. And through that talk, I would indeed like to show that, in fact, the domains are very close, and there are very beautiful math and signal processing problems arising from machine learning. So the talk will be more specifically about deep neural network, interpretability in the mathematical sense, so trying to understand the underlying mathematics. And for that, we'll look at a number of problems which will range from classifications to generation, not just for images, but also I'll speak a bit about physics. So the topic, you know very well what it is, high-dimensional learning. You want, for example, in the context of image processing, given an image X, so that's the image which is a very high-dimensional vector, typically about 1 million variable, you would like to associate a function f of x, for example, what type of object you have within the image. So, for example, car, mushrooms, and so on. Now, in physics, you have essentially the same kind of problem. X will be describing the state of the physical system. So, for example, in quantum chemistry, X would be the position of the atoms and the number of charges of the atom of the molecule. And f of x is a quantity associated to the state, for example, the energy. If you can learn the energy from a database, then it's basically very close to learning physics, since from the energy you can derive interaction forces through derivatives. So in machine learning, we do that from a database, supervised learning of xi, example of state, and the value of the function that you want to evaluate on these particular examples. The second type of problem I'll be looking at today are unsupervised training. So in that context, what you want to estimate is rather the distribution, the probability distribution of your data given a family of examples. So you have very well-known standard problems in physics, for example, turbulence, since the first papers of Kolmogorov in the 1940s. It's still a mystery to be able to model a turbulent fluid and find out the properties of the probability distributions. But nowadays, you have much more impressive and strange applications, such as, can we define a random process whose realization would be phases? So you have a totally non-ergodic, non-stationary, non-Gaussian, non-nothing, essentially, random process. Does it make sense? What does it mean to compute random realization of such a random process? Now, the common point of all these problems is the fact that we need to estimate a function of a vector x, which is in very high dimension. And the reason why all these problems are so difficult is because of this curse of dimensionality, which again, I'm sure you all know, but I'd like to come back to it because it's very fundamental to understand the difficulty of all these problems. If you look at the problem, essentially, you have a simple interpolation problem. You know the value of your function at the different point xi. You are given a new x. You want to know the value of f of x. So the immediate reaction that comes to mind is to say, well, the value of f of x, I can compute it by averaging the values for the different xi which are close to x. So compute some local interpolation. Now, the reason why that never works in high dimension is that you essentially never have a close neighbor. And the reason why you never have a close neighbor is because the size of the domain is absolutely huge. Take a cube, 0, 1, in dimension d. Suppose that you want to make sure that you have an example which has epsilon away from the point x. That means that you need to sample your cube uniformly, and the number of points that you'll need is epsilon to the minus d. Now, if you take for epsilon 1 over 10, which is not so small, d 100, you get t 10 to the power 100, which is already more than the number of atoms in the universe. And the difficulty is obviously d is not going to be 100, but rather 1,000,000 or even more. So that means that the space is huge, and even though you may have millions or billions of examples, it's just very few isolated points in this huge space. So if you want to interpolate, you need that your function is incredibly regular so that from few sparse points you can predict the value of the function at any point x. Now, you may be lucky and x may not live everywhere in the space. That's an important piece of information. It may be concentrated in a subdomain omega, but in all the problems we are going to consider, omega is very high dimension. So understanding the regularity of f is the core problem from a mathematical point of view. Now, the reason why we are looking nowadays at this problem in such generality is in particular because of this amazing success of convolutional networks. So I suppose you all know, again, what it is, but let me briefly summarize and set up the notation. So I'm going to consider applications of images because it will be much simpler to get an intuition for what's happening. So the input x here is an image, and a convolutional network alternates convolutional operator, which is a linear operator here, whose support is typically quite small in the image, let's say 5 by 5, and the weights are invariant to translation. And then you apply a nonlinearity, which in most cases will be a ReLU. So the max of the value and 0 will be taken at the output of the convolution. Now, at the next layer, things get a little bit more complicated because the value of one point here will be calculated through a convolution kernel for each image. You are going to sum up the convolutional value, and you'll get the value of your intermediate layer here. You do that for very different type of convolution kernel, you get the next layer. Potentially, you subsample, so you get smaller images. You continue such convolutional subsampling up to a representation which is here the last layer, which will be typically a lower dimensional representation compared to the input image. That's what I call here phi of x. And then you do a simple linear combination to get an approximation of your high-dimensional function. So the number of parameters of this network corresponds to all the convolutional kernel, and typically you have hundreds of millions of parameters, which are optimized so that the output of your network is as close as possible to the true value f of xi, so you do a stochastic gradient descent on the loss function. Now, what is quite amazing is that these networks have impressive generalization abilities, not just for image processing, but also for speech, also for translation, regression in physics, image and signal generation. It looks like there is something very generic, even beating the world champion of Go, behind this architecture to approximate a very wide classes of functions. So one of the questions is to understand what is in common between all these problems so that a single type of architecture can approximate them. Right now, we essentially don't understand the why. How come these structures are so efficient? And the goal of the lecture will be to try to shed some light on these questions. So there's two core questions one can ask. First of all, as I said, the function to be approximated needs to be very regular. What kind of regularity these networks are using to do the approximation? The second thing, it looks like everything is being learned, but the fact is you have a fixed architecture to begin with. So this fixed architecture encapsulates some prior about this problem. What are the role of the prior? What are we really learning through the learning of the weights that you could not incorporate within these priors? Now, what I'm going to try to show is that there are at least three key properties which arise in these problems. The first one is scale separation. When you look at a network like that, initially you aggregate your variable on a very small neighborhood, and then you subsample, reaggregate, so you aggregate of a broader and broader neighborhood, and that allows you to incorporate elements at different scale. You can view depth as a kind of scale axis. Second thing, within these networks, some of the neurons, when you go at relatively large depths, begin to be totally invariant to transformation of the input. So you'll see the notion of invariance over groups of symmetry. Sparsity. A lot of answers of the neurons are very often zero. Why is sparsity playing such an important role? So we'll look at different types of applications. In some sense, the simplest applications is modeling ergodic processes. Still very difficult, as I said, it's still an open problem for turbulence. There is a very nice set of papers by Matthias Bedge and their collaborators, where basically they try to reproduce textures, so images such as these ones, which represent turbulent flow or bubbles. And the way they do it, they take a network which has been trained on a database, ImageNet. Then they take one such image they want to model, let's say this one, decompose it in the network, measure the coefficient of the image, then at any given depth, they measure the correlation between the coefficients at different channels, and then they resynthesize a new image by trying to match these statistics. They begin from white noise, progressively update the image until they have the same statistics, and they produce new image which looks like realizations of the same random process. If the input is this one, they get images like these ones, or this one, depending upon the input. What's happening? What is the mathematical interpretation? What kind of model can we have? Even more sophisticated image generation, autoencoders. You take an input image, if you take, for example, a Wasserstein autoencoder here, you have a network which is going to transform this image into a low-dimensional white noise. And then this encoder, which is a deep net, is inverted to try to build an approximation of the original image. So the two networks are learned together with a condition that this should be nearly a Gaussian white noise. Now, if you have a random new noise, once the network is trained, let's say, on bedroom image, you can generate a bedroom image. With another noise vector, you generate, let's say, another bedroom image. And the impressive thing is that if you make an interpolation between these two noises, any intermediate noise, if you reconstruct, you still get a bedroom. As if the images of bedrooms, which corresponds to an incredibly complicated set of points in the original space, has been completely flattened out so that the average of two bedrooms is now a bedroom. What's happening? What mathematical model? So these will be the questions. Now, the core, very important idea that will be behind all that will be scale separation. So I would like first to begin with this idea, which will drive a lot of the talk. In very high dimension, the difficulty, let's say in physics, you have n particle or d bodies interacting, is that all particles can interact with all others. So these particles, you can view it as real physics particles or agents in a social network or pixels in the image. Now, if you look at the interactions, very often the very strong interaction, let's say with the red particle, will be the neighbors. Let's say your family or the close pixels. Now, the more far away particle, you can summarize their interaction on this one by looking at the equivalent field they all produce. So you don't need to look at each interaction. The even more far away particle, you can summarize them with a bigger aggregation over this one. For example, if you want to look at the social network across the world, you don't need to know what will be the influence of a certain person in China over your life. It's negligible. But on the other hand, you cannot neglect the set of all Chinese which form China, because if, let's say, China has some political tension with the US, that may affect your life. So groups appears as being the main thing. And groups, how many do you have? Log D. And if you think in terms of groups, multi-scale groups, you can break this curse of dimensionality. Now, scale separation, we know how to do it. And that will be the role of wavelet transform. What is very hard, and which is still open since the 90s, is to understand how scale interact, how all these groups interact. And strangely enough, I'll show you that deep networks have, seems like, an answer to that question. So there will be really three parts in the talk. The first part will focus on scale separation, and I'll try to show why rectifiers are so important, and the fact that, in fact, they build interactions across scale through phase. And we'll see applications to try to understand how to model random processes which are not Gaussian, such as turbulence. The second part will be about the second concept, invariants. Why invariants are so important for classification and for regression. How do you build invariants, and how does that naturally lead to deep network structure? The last part will be really about learning. What would be the smallest minimum model that you need to learn in order to achieve the kind of results that we see with deep network? And I'll try to show that sparsity is key here, and we'll look at applications on classification problems such as ImageNet or synthesis of images such as autoencoders. So let me begin with scale separation. Scale separations, to build it, essentially, as Les was mentioning, will go through a signal processing path. How can you do it? The idea is to use, instead of sine waves, wavelets. So what is a wavelet? It's a small sine wave which is localized, a Gaussian, let's say, multiplied by a cosine for the real part and a sine for the imaginary part. And then, a bit like sine waves, you are going to rotate your wavelet. So these are your wavelets rotated. But you also, in order to capture different frequency, scale your wavelets. These are the very fine scale wavelets and coarser scale wavelet. This is the scaling factor. So what is a wavelet transform? It's a simple what is called filter bank. That means you take your signal and you filter your wavelets with all these filters at different scale, different orientation. Basically, you explode your information in terms of rotations and scale. If you look in the Fourier domain, as you know, a convolution in the Fourier domain is a product. Now, the Fourier transform of the wavelet is a bandpass filter. It's localized in some frequency band in my two-dimensional Fourier plane. There. What's happening if you rotate the wavelet? In the Fourier domain, the Fourier support is going to be rotated, so you are going to have different frequency channels like that. If you scale it, in the Fourier domain, it's also going to be scaled. And what you see is that basically you are dividing your Fourier space into different frequency bands, which corresponds to different orientation, different scales, set of filters. Now, if you want to model a stochastic process, which is stationary, what's the problem? The problem is that when you measure your wavelet coefficients at two different scales, they are going to appear as if they were not correlated. The correlation coefficient between two different frequency bands, you can prove it by looking at the Perceval formula, because the Fourier support are disjoint, is always going to be 0. So let me show you what that means. Here you have an image. So how do you compute a wavelet? You filter with, let's say, your sine and cosine, different orientation. Gray here means 0, white positive, black negative. You see you have large coefficient essentially near the edges. And you get your average. You subsample, then you again take the average, you filter it, you have the high frequency, the low frequency here, like this. Now these are the different frequency bands. If you look at them, they look very similar, very dependent. But if you try to compute their correlation, it's 0. Because the phase fluctuates randomly. So you cannot capture the dependence across frequency, and this is why it's such an old problem, if you just go linearly by computing correlations. Now, what would people do in physics if they're facing a problem such as modeling turbulence? So, this is a turbulent fluid. The standard approach is to say, okay, I want to model a probability distribution, and for this I'm going to make measurements. And these measurements will be the expected value of your turbulent fluid transformed by some nonlinear function phi m. So you have a set of moments, and then you want to compute a model. And the way you'll compute a model by saying you want to find the probability distribution which has the same moments, but which has a maximum entropy. And if you set up this optimization, you can show your probability distribution will have an exponential form, and these are the Lagrange multiplier. This is how you approach problems of modeling random fields in statistical physics. Standard way to do it, for phi m, you just look at the correlation of your image at two different points, which are a little bit away by translation m. That means this is a bilinear form. You put it here, and you verify you have a Gaussian model. How does it look like? Like this. This is the Gaussian model. This is, in fact, the Kolmogorov model of turbulence. And you can see that it has completely destroyed the geometry. DeepNet were able to do much better than that. Now, in the 90s, what people have been thinking in statistical signal processing or in statistics, well, second-order moments are not enough. Let's move to high-order moments. And there was hundreds of papers on that, and that was essentially a failure. It was a failure because you have much too much high-order moments, and to estimate these high-order moments, you have a huge variance. So how come deep networks are able to do it? Let me come back to these wavelet coefficients. So these wavelet coefficients, they are complex. They have a modulus and they have a phase. Let me specify the phase by, let's say, fix a phase alpha by introducing a real wavelet by taking the real part of my wavelet shifted by alpha. Let's do like a deep net, where in the network, I would have a real filter, but here I'm going to impose that the filter is a wavelet with a phase alpha. So if you do that, you do the convolution with this filter, you are going to get the modulus, and instead of a complex phase, you are going to have the phase with a cosine shifted by alpha. Now, what's happening if you put a relu on this, a rectifier? If you put a rectifier, the rectifier is not going to affect at all the modulus because the rectifier of alpha A is alpha rectifier of A. It's just going to affect the cosine. What really the rectifier is doing is essentially putting a window on the phase. It's eliminating all the coefficients which are too far away from the phase alpha, setting them to 0, and the others you multiply it by a window, but you preserve the modulus. Now, because you do this phase filtering, in this case with the rectifier, now this is positive, this is positive. If you do the correlation, it's non-zero. What you are going to be able to do is not just correlate frequency, but correlate frequency with the phase alignment. Let me show you what that gives. If you take the same images, and that's the work of Sixin-Zhang, these are images which are random fields. Instead of taking d moments, these images like you would do for a Gaussian model, I'm going to take much less moments, only log d, okay? Just for each of them, one correlation. I'm going to correlate these wavelet coefficient with the rectifier with another wavelet coefficient with themselves a rectifier. You know that in this case, this is the phi m, so that will be the model. If you look at a random realization of this model, that's what you get. You recover images which have the quality of synthesis of deep network. Here you have a mathematical model, you know exactly the probability distribution, you need much less moment. What was the key property here? Coherence of phase. Because of the relu, you can realign the phase between the different frequencies. And from there on, there is a lot of interesting math to understand. In the case, so these are different physical phenomena. Ising is a ferromagnetic problem, is to try to understand why, what kind of underlying physics you have. But let me move. Let me move to classification. There is one element which is also very important besides scale separation when you deal with classification, is the fact that you have invariant property. If you take an object, oops, let's take this one. If you translate it, it's the same object, obviously. If you take a digit, 3, you translate it, it's still a 3. So essentially, most classification problems are invariant to translation. Translation, this defines a group, but translation is only specified by 2 parameters. So if you kill translation, you go from a space with 1 million parameters to 1 million minus 2. Big deal. You need to find invariants to much bigger groups. Now, there is one group which is very important, is deformation. If you deform a 3, it's still a 3 if the deformation is small. A 5 is still a 5. If you take European paintings in the Louvre, you can like that travel across all of them by moving on the groups of diffeomorphism. As long as the deformation is small, you'll recognize the same painting. When the deformation is too big, then it's a different one. So you can kill all the deformations as long as these deformations are not too big, and you'll need to find which one they are. How to do that? The strategy is try to linearize the action of this deformation and then kill the deformation with a linear operator. And that's what we're going to look at. What I'm going now to show is that dealing with these invariants and this deformation naturally leads you to a deep network. But this network will be a little bit simple. Simple in the sense that you are going to have a kind of tree, successive filterings, like in a filter bank, with rectifier, but no interactions between channels. So when you look at this problem from a math point of view, it's always simpler to begin with simple model. But of course, if you have a simple model, the question is what are you going to lose? And that's what we're going to see. What's the limitation of not learning the filters? And how much are you losing by doing that? These will be the different questions I'm going to try to address here. Okay, so let me begin with a simple problem. You have a function x, and you want to build an invariant to translation, and suppose that you impose that this invariant should be calculated with a linear operator. What can you do? Well, you can show, in fact, you have no choice. The only thing you can do is average your function. If you average it with a filter like that of a domain of size 2 to the j, you are going to regularize it, and you are basically going to be invariant to very small translation. If you want to be global invariant, you can. You need to globally average it, and this is invariant to translation. Now, the problem, of course, is that, great, you're invariant to translation, but you've lost nearly all the information. So the questions when you build invariants is to build invariants which are rich enough. The problem is that if you are linear, you cannot move from there. So where did you lose information? You lost the high frequencies. How can you recover the high frequency? With bandpass filter, with wavelets. Now, this is the answer of a one-dimensional wavelet transform. If you average that, you get 0. So you need to put a nonlinearity, and we're going to put a rectifier. If you rectify these coefficients, you only get positive coefficients. Now, you can average, and you are going to get a non-zero coefficient. Now, for any frequency, you now have a new family of invariants. On the other hand, you've again lost information because all the wavelet coefficients, you average them. If you want to recover the information you've lost by producing more invariant, what can you do? Well, you can take your wavelet coefficients and instead of averaging them, extract the high frequencies that you've lost by doing the averaging. If you do that, you are going to get these wavelet coefficients that now you can again rectify, average to get a new set of invariants. What have you been doing by progressively computing these invariants? You've been computing a deep net. This is the wavelet transform. This is the rectifier that you put on each of the coefficients and the average. Now, each of these images, if you want to build a new invariant out of it, you are going to average it and apply the rectifier, and you are going to get these other images which are here, which are the wavelet coefficients. If you want, again, to build new invariants, you reapply a new wavelet transform, and so on. So you have a cascade of wavelet transform rectification, that builds you an operator here that we call the scattering operator, which is nonlinear, which is a cascade of nonlinearity, convolution nonlinearities, and so on. Now, observe, contrarily to deep net, there is two differences. I don't learn the filter, simplistic, and I don't build any connection between channels. This is just a tree. So you can, because it's simpler now, try to analyze the property of what you have. It's a cascade of operators which are unitary, linear, simple, and a ReLU is a contractive operator. You cascade such operators. The first thing you can show is that you have a representation which is stable. The output of your network for a signal x and y, their distance is always smaller than the distance between x and y. Okay, nice, but no so fundamental. What is really very important is that you are linearizing all the deformation. If you have an image x, if you deform the image by moving the points of the image with a function tau of u, if you look at the output of your network on x and the output of the image deformed, the distance is going to be of the order of the size of the deformation. So in the space of your coefficient, a deformation is going to act as a Lipschitz operator, something which is very regular. This is key for classification. So how can you do classification out of that kind of thing? You build your network, no learning here, and the average. So that's the network with wavelet filters. And from there, the only thing you learn is the last layer. The last layer is a simple linear classifier, okay? And then you can try to apply that on image data. So the first very simple example is MNIST. You have a database of digits, 10 classes. Within each of the class, what is the source of variability? Essentially, translation deformation. So it's a perfect problem. And you can verify that whether you use a deep net or a wavelet scattering transform where all the filters are predefined, you get the same result. Why? Because this is an example where essentially you have enough prior information to specify the problem. You can try on textures, same thing. You will not lose by not learning the filters. You can try on quantum chemistry. So I'm not going to detail that application, but this is an application where you want to learn the energy of a molecule. The energy of the molecule is invariant to translation, invariant to rotation. You can incorporate this prior information by designing the appropriate filters, and then you get same precision than deep networks. But if you move to something much more complex, such as ImageNet, it's a catastrophe. The error is 50% if you just do it with wavelets. If you do it with AlexNet, that was 2012, you get an error of 20%, and the more recent ResNet are about 5% error. So obviously, you are missing a big, big part when you begin to have much more complex problems. And the question there is, what is learned? So that was a difficult problem for me. Why? Difficult for many reasons. The first one is that I did about 5 years ago a bet with Yann Lequin by saying, look, within the next 5 years, someone will come out with a solution for ImageNet without learning. And 5 years, now, betting is okay, but I made the mistake to bet a 3-star Michelin restaurant. And 5 years afterwards, I lost, so I had to buy a 3-star Michelin restaurant to Yann Lequin at the same time that he got his Turing Prize, so it was totally unfair. But that's life. And at least I got one question out of it, which is a nice research problem. Okay, something has to be learned. What has to be learned? What is the minimum amount that you can think of that you should learn to breach and go beyond AlexNet? Now, if you, and that's my third and last part. If you think about this domain was called pattern recognition before. So what is pattern recognition about? It's about finding patterns in a signal. How can you think of a pattern from an applied or mathematical point of view? You can put all your patterns in a dictionary. So any column of this big dictionary matrix here is one of the patterns you may be looking at. And to decompose a signal x into patterns, you can view it as representing x as a product of d multiplied by a vector z, where the coefficients of z are 0 outside few coefficients, which corresponds to the selected patterns to reconstruct x. This is a very standard problem. There are many techniques to solve that. At the time, in the 90s, I was working on it with matching pursuit algorithm. Then David Donohoe proposed an L1 formulations. How can you compute the sparse code? You want to approximate x so that the approximation with dz is near 0. But you want to make sure that z is sparse by doing a penalization with an L1 norm. And here I'm going to impose also that z is positive to indicate that, in some sense, you select the patterns with its sign. This is a convex minimization problem very standard, many algorithms to solve it. One of the type of algorithms that we're going to use here are homotopy algorithms. And the strategy we're going to follow here is to take these algorithms, transform them into a network, and then use that for learning. So, and that's an idea that has been around. A number of authors, such as Miki Elad, have been trying to represent deep sparse coding within deep network. So a homotopy algorithm, the idea is the following. Instead of fixing the optimal alpha, you begin with a very large alpha, compute the solution, and progressively reduce the alpha. To minimize such a quantity, you can do a gradient descent. If you take a gradient on the first term, you are essentially going to get that kind of matrix, identity minus D transpose D. You also have the L1 term here. If you do, in some sense, a gradient on that, it will be a proximal operator. What you can show is that it essentially amounts to apply a rectifier. A rectifier with a bias, and the bias corresponds to the weight. So here, the rectifier is going to play the role of the proximal operator in my optimization problem. You can show under appropriate hypothesis that that kind of algorithm will be exponentially converging to the optimal solution. So what's the relation with the deep net? What do you have here? A linear matrix followed by a rectifier with a bias. So that's a deep net, okay? That's my rectifier with the bias, linear matrix, and then you have the sum, a bit like residual network, and rectifier, the bias, and so on. How many times you are going to do that? The depth of the network corresponds to the number of iterations, and that's why it's very important to have a converging algorithm which is fast. Okay, so how do you incorporate that within a classification problem? The idea is the following. And again, that's ideas that were developed in particular by Meral and Pons quite a long time ago, learning dictionary for classification. Here we're going to do it with these iterative thresholding network. You take X, you compute the sparse code with your network. Your network has many layers, but a single matrix. The only thing you are going to learn is a single matrix D that you are going to repeat for each layer to build your sparse code. About 12 layers. You have a classifier, and you get your result. Okay, so what does it mean learning here? Learning will be about learning the patterns. Learning the patterns means learning the dictionary. So you are going to learn both the dictionary and the threshold in order to minimize the classification loss with a stochastic gradient descent. This is a totally standard deep net algorithm. Just the architecture is a bit particular because there is a single matrix that you are learning here. You can verify that your algorithm converges very fast, but that's technical optimization details. Okay, let me show you the result. So if you begin with just scattering, classifier, you get an error about 50%. If now you take X, you do a sparse coding, classifier, same result, no improvement. If now you take the scattering transform, you do a sparse coding on the scattering transform, you have a big improvement for more than 30%, and you beat that extent. What's happening? You see here, the reason why dictionary learning doesn't work on your image is because the image has too much variability. You have deformation, translation, rotation. So in your dictionary, if you have one pattern, you also need to store the pattern deforms, translated, rotated, and so on. If you build invariants or you linearize all this through the scattering transform, any deformation is a linear operator. You don't need to encode it anymore. You just need to have a dictionary of invariant pattern. So the dictionary can be much smaller and much more effective. And that's how you get such a big improvement. Now, how can you think about it? you can think of it as a kind of clutter removal. This is the representation of the scattering transform as a deep net layer. The dictionary learning, we do it with a 1-1 convolutional matrix, which is your dictionary. Basically, what it's computing the channel communication that we completely ignored in the case of scattering of the neural network. Now, if you do the classification from DZ, which is the approximation of your input scattering coefficients, you will see that, in fact, the approximation is pretty bad. The reason is that when you optimize the threshold gets very big. Essentially, this network acts as a clutter removal. It removes a lot of the variability of the signal, which is useless for the classification. The relative error is about 50%. So it's not like in denoising when you want to reconstruct exactly the signal. Here, you are really eliminating information. Then, at the classification stage, what you can show, and that we verified, is that once the classification, for example, a linear classification does a projection, you see a very strong concentration of each of the clubs. So the elimination of all this clutter is what allows the classifier to then concentrate. Why what's happening? Not very clear, but at least we do observe that. And let me finish with the autoencoder. My goal here, by going through all these topics, is to show that essentially you have the same mathematical concept which are going through in the same way that you have the same kind of architecture. The autoencoders are quite a fascinating problem. You begin with a stochastic process, which is an image. Realization is an image. It is transformed in something that looks like white noise. And then the generator restores an image. And all this is trained over a database so that for each xi, you reconstruct something close to the original image. And I showed you these examples on database and the fact that it linearized transformation in the embedding space. OK. How can you specify the problem mathematically? You begin with a random process X, which lives in high dimension. You found an encoder, phi, which transforms X into phi X, which is now a Gaussian process. But it lives in a much smaller dimensional space. Typically, this is 100, whereas this can be of the order of 10 or 100,000. And then, from this low dimensional vector, you reconstruct X. So you have an inverse problem. Okay? What we are going to try to impose, if the inversion is stable, is that the encoder is invertible and stable Lipschitz. So that means that the encoder is by Lipschitz on the support of X. Not everywhere, just it's able to reconstruct X. So that's a well-stated problem. Can you find a by Lipschitz map which transforms X into a Gaussian white noise? Nice problem, but totally untractable. Totally untractable because you don't know the distribution of X, unless you do something very brutal. In high dimension, there is only one mathematical tool to transform a random process into a Gaussian process. It's to average. It's to mix your random variable. Central limit theorem. You take your variable, you mix them by averaging, and if you have a little bit of independence or decorrelation, it's going to converge to a Gaussian process. But if you do that, you are going to end up into a much lower dimensional space because you've averaged everything. So under what condition can you reconstruct X? It has to be very structured to be reconstructed so that you can reconstruct it from a low dimensional approximation. What we're going to suppose is that X is a particular kind of random process which can be compressed, namely which has a sparse representation. So we are going to end up with the same kind of dictionary learning problem, same kind of architecture. Last property, if you take faces, you take bedrooms and so on, You deform it, it still looks like a face, a bedroom. Stability to deformation. That's the other prior you have. So, once you have these prior, you can try to solve the problem. Input x, you need to whiten it. To whiten it, you're going to average. But before, you're going to separate all the scales with a scattering transform to have something which is stable to deformation. You make the convolution with the wavelet, you apply your ReLU, and then you average. The average is what is going to Gaussianize your random process. You're going to get, hopefully, something Gaussian, and then you need to make it white. To make it white, it means that the covariance matrix has to be identity. You can do that with a simple linear whitening operator. So that's what you're going to get. Scattering transform, and then a linear operator. OK. The difficult part is the inversion. Now, you have your low-dimensional pseudo-white noise that you've computed from X, and you need to reconstruct your bedroom from that. OK, why is it difficult? What is difficult is not this part, you see, because this part is a wavelet transform, this is invertible. The rectifier, it's invertible, because rectifier of A plus max of minus A, that gives you A. So if you have two phase, boom, you invert the rectifier. What is really difficult is because of the linear operator, which has Gaussianized everything. In other words, your operator which has averaged and produced a low-dimensional approximation. So for this, to invert that, we are going to use a very standard approach. Some call that compressed sensing, sparsity. OK, what's the idea? So you begin from a low-dimensional vector. Think of it as a 100 dimension. That will be typically the case. And you want to go to dimension 10,000. What I'm going to suppose, and you see it will be exactly like in classification, is that I can sparsify my scattering coefficient. In other words, in some dictionary that I don't know for now, I can find a sparse code Z so that UX can be approximated by DZ. If that's the case, remember the white noise, and what I'm describing here is the standard inverse problem approach when you have a sparsity hypothesis. Your white noise was obtained from your scattering coefficient by applying the operator L. So if you plug here DZ, you see the white noise can be written from the sparse code with a linear operator. So that's the network. You begin with your white noise. You try to find a sparse code in the matrix LZ, is with iterated thresholding network that I described previously. You get the sparse code Z. From Z, you reconstruct UX by applying D. And then you invert U, and you get X. What is D? D is the memory. In an autoencoder, you see appearing, so we will, again, only learn one matrix, but this matrix will be the memory of your autoencoder. How do you learn this memory D? You just try to optimize D so that X tilde is nearly equal to X, exactly like in an autoencoder algorithm. This is an autoencoder algorithm. We optimize. The only difference is that the coder is fixed. It's only the decoder that you optimize. And in the decoder, you only have a single matrix to learn, which is a dictionary. So you do that. Let me show you an example on faces. These are your database of face. You have about 5,000 to train, 3,000 to test. So that's the training images. These are the reconstructed images. You optimize the dictionary to reconstruct them. So it's not very surprising that you reconstruct a good approximation. Then you take new images that has never been seen in your network. You try to reconstruct them with the same dictionary. And basically, you get exactly the kind of results you get with a autoencoder. You get good recovery approximation, but there are some fine details that are lost. Why? It's exactly like in a compression problem, because you fix the size of the dictionary. So you have a limited amount of coding abilities in some sense, and you commit errors. Then you can test deformations. This is an image reconstructed from white noise. This is an image reconstructed from white noise. You do a linear interpolation of your white noise, and these are images reconstructed, and you see you have exactly the same type of morphing properties. The reason is that your operators that you've used in your encoder has this Lipschitz regularity to deformation. It preserves deformation properties. You can try on another image to this one, you have the same phenomenon. And then synthesis. So now you produce a random white noise, low dimensional, you send it through your encoder, and you get that kind of reconstructed image. So these are random faces. So this is, again, nothing surprising for people who know the autoencoder. It's an autoencoder. The only thing I'm trying to show is that this is not a completely crazy esoteric idea. You can view it just as a standard inverse problem where you've been learning your dictionary to do the sparsity, and this dictionary captures the property of your random process. If you think of it, it's like almost an autoregressive process. You know, in an autoregressive process, you take your Gaussian process, you whiten it, and then you reconstruct with your autoregressive filter. Well, this is a reconstruction. The only thing is that Gaussianization is needed, so you have a reconstruction which is very nonlinear. Okay, so let me conclude on all this. There is several things I think we can say about this deep network, many, many things. One view of them is, I don't think that the goal of theory here is to understand all deep networks. Why? Because I think we can view these networks in some sense like Turing machines. They have an amazing flexibility in the same way that you can program nearly all what you want with the program of a Turing machines. When you optimize all the weight of a deep net, it can do many, many different things. But if you want to make a program which has no bug, then you'd better not make a code with 5 million lines, which in a totally unstructured way. What do? You structure your program with specific function that you can debug independently. I think that the same kind of thing will come into DeepNet. We can see that there are different functions in what I described. Like the first part of the network, the scattering transform, was essentially linearizing the actions of symmetries. The second part was the sparse coding, which was able to capture patterns. There are many other functions, I'm sure, that can be implemented with that kind of network. But once you've understood that, you can completely debug each of them, and you can interpret. You can interpret in one sense. I didn't insist so much about that. Once you know that the only thing that you learn is a dictionary D, you can go within the dictionary and you can look at the type of patterns that has been extracted to specify the classification or the model of the random process. So from a math point of view, I think the problem is very open. It's very interesting because there is a mix of many different types of math, obviously optimization, harmonic analysis, which comes through these multi-scale separation, group theory through the notion of invariants and symmetries, and of course optimizations again, and approximation theory through the notion of sparsity. However, I mean, we are just at the infancy of this problem. Really what we would like to do is to do the same kind of thing that we do in math in low dimension. If you have a function, you can specify the regularity in many ways, derivative. You can say your function belongs to a sub-Left space, a Bezoff space, and you can exactly specify the number of parameters needed to approximate your function with an error that decays to 0 with a certain rate. You'd like to have the same thing for DeepNet. Specify the class of function, say how many neurons you need to approximate your function with a certain error, and how fast it will decay to 0. And all this, at that point, we are very far from it, so there are still very beautiful problems to study. Thanks very much.
Well, we have a little time for questions, a few questions.
Yeah.
Oh, no, he can say after.
Okay, yeah. So deep nets are notorious for needing a huge amount of training data. When you reduce the number of free parameters the way you did, do you need all that training data, or are you able to get the same kind of accuracy but with less training data?
Okay, so do we need as much training data with that kind of network? We did the experiments on MNIST and in quantum chemistry. When you specify the scattering transform, you can reduce the amount of training data. Now, when we learned the dictionary, we didn't look at it, and it may not be so clear. Because it's not because we learn a single dictionary matrix that we have much less parameters than the overall network. So that has to be studied. But in general, I think your point is totally right. If you structure better the problem, you should be able to reduce the amount of training data, and that's indeed pretty crucial in number of applications.
One more question? Yes.
So I just wanted to make sure that I understood. Can you think of the analysis that you did stage-wise, where you first generate features using the scattering transform, and then completely separately from that, you solve a standard dictionary learning problem from those features to then do the classification? Is that the...
That's exactly the way it's done. So you first separate scale linearize and then do the dictionary. That's not to say that that's the ultimate way to do it. I have a tendency to think that, in fact, you want to embed the two. Probably you want to go up to a certain scale, compute dictionary, because you know, the notion of patterns is not multi-scale. You have patterns at the scale of the face, patterns at the scale of the body, at the scale of this room, of a house. So very likely you want much more to embed. But the point is, learning we may be able to reduce learning to a very standard optimization problem, which is dictionary learning, which is still a very difficult problem, non-convex, but at least mathematically very well defined.
If I may, one more. You indicated that the ReLU function does a localization, if I understood right, in phase space, which was key for computing correlations. How much room is there left for optimization of the nonlinear dynamics at the individual nodes, namely replacing ReLU with something else in order to optimize the performance of the network?
Okay, so maybe I'm going to, so the question is, in what sense ReLU is optimal? Can we further optimize the ReLU? The ReLU has one advantage, is mathematical simplicity. It's a homogeneous functions. You can do everything. Now, much simpler calculation with it. Now, another nonlinear function will have a similar role in the sense that another nonlinear function will reproduce harmonics and have similar behavior as a ReLU. On optimization, it looks like ReLU has better property, but it could be that one can improve results by, and some people have tried, by modifying the ReLU. From a math point of view, I think the problem is hard enough with ReLU. Let's stay with it. That's a little bit my tendency. But that's not a good argument from application point of view.
Well, let's thank our speaker.